So let's do a stereotypical inclined plane problem. So in physics, if you've ever taken physics before, you certainly have heard of inclined planes. So we got to do an inclined plane problem. What is that? Well, that is, let's put an object, instead of on a flat surface, let's put it on a plane with an incline at some angle theta. So for example, it could be a child on a slide, it could be a car driving up a hill. Instead of making it curvy, we're just going to make it a flat hill, at least to make our lives easier at first. Or it could be a conveyor belt system moving boxes from the second floor to the first floor. So let's just say we have a box of mass m, and it is sliding down an inclined plane. Let's start with a frictionless inclined plane and just ask, what is the box's acceleration down the plane? So start with that. What is the box's acceleration down the plane? What is box's acceleration down the plane? Let's say that we're a cereal company and this is a box of Cheerios. Box of Cheerios is sliding down this plane, and we could give it numbers if we wanted. Let's say that the mass is 2 kilograms and theta is 22 degrees. No, they're all 2's. Let's make it 35 degrees. 35 degrees. And ask, what is the box's acceleration down the plane? Well, let's go ahead and do a Newton's second law problem. What are the forces on the box? What are the forces on the box? First of all, I'm going to draw the box independent of the ramp. I'm going to draw it at an angle just so I remember it's on an angle. I'm going to say that what are the forces? Go through your catalog of forces. Is there friction? No, we made it frictionless. Is there a rope attached? No, there's no rope attached. Is there gravity? Yeah, there's gravity. Gravity is always straight down, right? The gravitational force equal to mg, always straight down. Is there a normal force? Yes, there's a normal force because it's on a surface. What's the direction of the normal force? Careful. The direction of the normal force is always perpendicular to the surface of contact. So that's why I made sure to draw the box at an angle, because the direction of the normal force is going to be at an angle like that. Okay. So are there any other forces? We've gone through our entire catalog, Ft, Fn, Ff, Fg, any additional pushes or pulls that we didn't think to take into account. There we go. That's our free body diagram. That's a complete diagram of the box. And now let's choose a positive direction. In order to solve Newton's second law, we've got to choose our axes, positive x, positive y. And now we're in a quandary, right? Because now we're not horizontal and vertical, we're at some angle. So what direction do I want to choose as positive? Or what directions do I want to choose as positive? Right, x and y are two perpendicular directions because this is a two-dimensional motion problem. Right, our vectors are in a plane; they're not in a line. If our vectors were in a line with each other, then we could do it in a one-dimensional problem. But this is a two-dimensional problem. So we need to choose our coordinate axes, and it's a two-dimensional problem. We need to choose an x and a y axis. So you might have a tendency to want to say, x direction is that direction, the y direction is that direction, because those are your standard axes. And that would be absolutely fine. You could absolutely apply Newton's second law, F net equals ma, using those or any other coordinate axes. But what you should notice is, what I was going to say, scratch that. But the advice is, in order to make the math the easiest possible, that instead of choosing your axes like that, it makes more sense to choose one of your axes in the direction of the acceleration. So imagine now, I'm going to add something to the free body diagram that does not belong in a free body diagram, and that's the acceleration. We know that this box of Cheerios is going down the plane. It's going in this direction. So we actually do know that it's going to accelerate down the plane. And in order to make the math the easiest, in order to make F net equals ma, which is a vector equation, easiest to apply, it is actually easiest to choose your axes instead of the axes shown, is to choose your axes so that one of your axes is pointing in the direction of the acceleration. And typically, just to do something the same every time, I'm always going to choose the plus x direction to be the direction of the acceleration, and the plus y direction to be perpendicular to that. Now, this, you got to be careful here. Right? So now the plus x direction is down the plane, plus x. So what direction is the plus y direction? Vertical? No, those are not at 90 degrees, right? Those aren't at 90 degrees. It's not vertical. So that means the plus y direction is going to be perpendicular to the plane. The plus y direction is in that direction, or in that direction, right? Perpendicular to the plane. Or it can be perpendicularly down. It could be that direction, right? Either one or the other, not both. But so in order to make the math the easiest, in order to make it most straightforward, we're always going to choose the plus x direction to be the direction of acceleration. Now, if you don't, so we're going to get to some problems where you're not sure whether the acceleration is, for example, up or down the plane. If we're not sure, we just guess, and it's still going to make our life easier. We just say, oh, I'm not sure it's up or down the plane, so I'm just going to choose plus x being down the plane. If I was wrong and it's up the plane, I'm just going to get my acceleration to be negative instead of positive. But if I'm right, if I know the direction of the acceleration, that means my acceleration is always going to be in the x direction, and it's always going to be a positive number. So we want to get into the habit of choosing our plus x direction not to be horizontal and plus y to be vertical, but our plus x direction to be in the direction of acceleration of the body of interest, and the y direction to be perpendicular to that. What that's going to mean is that the acceleration is always going to be in the x direction, and the acceleration in the y direction is always going to be 0. Right? If the x direction is the direction of acceleration, then the acceleration in the y direction is going to be 0. Okay, that's just for future reference problem solving and for this problem. Let's choose the plus direction to be x, and let's see why these things work out this way. So we've gone ahead and we've drawn our free body, we've drawn our picture, we've drawn our free body diagram, we've chosen our directions, and now what we want to do is, as always, because we've got vectors, we need to take our vector components along our axes. Now, so let's draw each of our vectors. Let's take our coordinate axis. We're going to take our coordinate axis and keep it at an angle because it's at an angle, right? The y is perpendicular to x, and they're both along and perpendicular to the plane. And let's say, for example, Fn. Fn is also perpendicular to the plane. So Fn, I'm having trouble drawing straight here. Hold on. Okay, Fn is along the y-axis. So Fn y is just Fn, is positive Fn, right? That's the y component of Fn. And Fn x, the x component of Fn is 0. There is no x component. Right? Fn is in the positive y direction. That's all I'm really showing. Fn is in the positive y direction. Now let's look at Fg. Fg points straight down towards the ground. Fg points straight down towards the ground. That's a G. And so Fg has an x and a y component, right? So we can drop a perpendicular to either axis, and we can see that Fg has an x component there and a y component there. So we've got, I can blow this up a little bit, we've got Fgx and Fgy. That says Fgx and Fgy. So we can take the components, but we need to know the angle. Which angle? Well, either angle, right? I mean, it doesn't matter which angle. We can find the components given either angle. But I think the natural angle to find is this one. Whoops, is this, oh my gosh, draw. Okay, is this one here. Now be careful. I'm going to redraw this a little bit more carefully. No, actually, yeah. Let me just redraw this a little more carefully. Just because we're going to do this a lot. So let's just make sure we get this. Plus x is in this direction. Plus y is in this direction. Let's go. Oh, gosh, come on, iPad. Plus y is in that direction. The ramp, right, was like this. That's the ramp. So that means this was the, whoops, not 30 degrees. 35 degrees. So this is the 35 degree angle. Fg points down this way, and so Fgx is this here, and FGY is this here. And yeah, I drew FGX and FGY in a different place, but those are still FGX and FGY. FGX and FGY, the components along the y-axis and the components along the x-axis. Okay, so if this is 35 degrees, then this angle here is 90 minus 35 degrees, so this angle here is 55 degrees. So this angle here is 35 degrees. So you need to do that. You need to look at the similar triangles and figure out what's at right angles, where are the angles. So 35 degrees is there. And so if this is FG, then the components are FGX is in the plus X direction, and it is plus FG times the sine of 35 degrees. Right? Because it's the opposite. FGX is opposite the 35 degree angle. And FGY, again, doing the geometry of the right triangle, is going to be in the negative y direction because it's pointing along the negative y-axis. Whoops, this is the negative y-axis. FGY is minus FG times the cosine of 35 degrees. We're getting that, just reminding you from SOHCAHTOA. Sine theta is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. We should be used to doing these kinds of things by now, etc. So that's where we're getting those from. Now you might have, let's go back to this picture here. Look at this picture here. If I use the purple angle instead, right, that purple angle, remember, that's the 55 degree angle here. Look at this picture where the 55 degree angle is, and look at this picture where the 55 degree angle is. I will point out that if you look at the right triangle that I drew in this picture, then we would say, oh, FGX, which points down the plane, must be positive in the positive x direction, is FG times the cosine of 55 degrees. And FGY, again, this is a different right triangle than this one. FGY, you can still see points in the minus y direction. That's the minus y direction. And FG, so it's minus FG, and it's the opposite side to the angle, right? It's the opposite side to the angle, so it's sine 55 degrees. And you say, but wait, you just told me FGX was sine and FGY was cosine, but look at the angle, right? You just got to do the geometry of the right triangle. You got to find yourself a right triangle, and you got to do the geometry of that right triangle, meaning calculate sine theta, so calculate cosine theta. If I choose the right triangle that I have in this picture, I get FGX is FG cosine 35, I'm sorry, FGX is FG sine 35. If I use the right triangle in this picture, I get FGX equals FG cosine 55. Why are they different? They're not different. Those are the same number. The cosine of 55 degrees is the sine of 35 degrees. Plug it in your calculator, you'll figure that out. Okay. So anyway, we've now taken the components. Components you should be able to do by now. I'm not going to spend a lot of time taking components from now on. We just spent a lot of time doing that here as a reminder. Okay, let's go ahead and now see, we've taken components. All right, so let's recap. So this is just taking everything. We drew our picture, we chose our axes, we drew a free body diagram, we took the components of all the forces, and that's just a recap. And now we are going to apply F net equals ma. We need to do that in the two vector directions. So we've got F, because it's a vector, we break it into vector components. That means F net x equals max, and F net y, whoops, we don't need a vector sign there. F net y, because it's one-dimensional now. We're breaking the two-dimensional problem into two one-dimensional problems. Tend not to use the vector signs. F net x equals max, F net y equals may, right? That's what F net equals ma means. We got in the x direction, F net equals ma. In the y direction, F net equals ma. So now it's a pure plug-in, and we say, okay, in the x direction, what do we have? In the x direction, we've got that and that for our forces. So therefore, F net x, the net force in the x direction from the free body diagram, tells us it's nothing for the normal force, and FGX, which is FG sine, sine 35 degrees, and that equals ma sub x. F net y from the free body diagram equals Fn minus Fg cosine 35. Fn minus Fg cosine 35 degrees, and that equals ma sub y. And then we say, okay, what do we know and what don't we know? All right, we know what FG is. That's the weight of the box. FG is just mg. We know the angle. We just wrote it as 35 degrees instead of theta. We know m because we're given the mass of the box. And we're looking for a sub x. That's what we're asked for. What we asked for a long, long time ago is we asked what is the box's acceleration down the plane. That's a sub x. We don't know f sub n. We know fg. We know theta. We know m. And do we know a sub y? Yes, we know a sub y. We chose our axes so that a sub y equals 0. The box is not accelerating perpendicular. It's not accelerating in that direction. It's only accelerating in that direction. So the box's acceleration perpendicular to the plane is 0. So we have two equations and two unknowns. One unknown, two unknowns, two equations, and we can solve. Therefore, let's go ahead and solve the first one for a sub x, since that's what we were asked for. Part A sub x is equal to fg sine 35 degrees over m, or mg sine 35 degrees over m, or g sine 35 degrees. The acceleration down the plane is just a component of the acceleration due to gravity. It's g sine 35 degrees. Notice that's just a component, the component of the acceleration due to gravity down the plane, right? So well, to some extent, we didn't really have to do all the work what we did. I think it was good to see how the problem is solved. But for any body that is accelerating in that direction, it's got a component g sub x and a component g sub y of acceleration parallel and perpendicular. I'm sorry, that's a little incorrect. It's not going to be accelerating in the y direction. But it's got a component down the plane because the plane's not in the way of g sub x, which is just g sine 35. Anyway, that was less important. So a sub x is 5.62 meters per second squared, or the acceleration is 5.62 meters per second squared down the plane, right? It's not in the it's not north, south, east, or west. It's down the plane. Really all I asked for, what was the acceleration down the plane? So the answer is 5.62 meters per second squared. What about the second equation? We never used it, this one. Notice, what does the second equation give us? Everything is known except for f sub n, so the second equation would allow us to calculate the normal force, which we never calculated or we were never asked for. I could ask part B, what is the normal force? And you can go ahead and calculate the normal force, and you can see if I asked, what is the normal force? What is Fn? And we can go ahead and calculate that from the second equation. Fn equals Fg cosine of 35 degrees, which is 2 kilograms times 9.8 meters per second squared times the cosine of 35 degrees, which is 16.1 newtons. That's the magnitude of the normal force, and I guess that was my implication, is what's the magnitude? The direction is perpendicular to the plane, up from the plane. Not up would be this direction. It's up from the plane, right? That direction, up from the plane. So I could say Fn vector up from plane, or perpendicularly up from plane.